So I've been working on integrating different types of phylogenetic data for the purposes of evaluating evolutionary history in birds and in squamate reptiles, which is just lizards and snakes. My major field of study has been phylogenetics, which is just the reconstruction of the evolutionary relationships between species and between higher taxa as well. One of the major types of data that we use for phylogenetic reconstruction is morphology, which is typically information taken from, for example, osteology, plumage, integument, morphology, etc. And this here is an example of an evolutionary tree or a phylogeny built for birds from morphological data. And on this tree, species are grouped together according to how morphologically similar they are to one another. The second major type of data that we use for phylogenetic reconstruction is molecular data or DNA data, which is typically much more abundant than morphological data in terms of number of characters that we can use. And it's also arguably much more objective in the sense that we can reduce it into roughly comparable units of equal weight. And we can also typically use more sophisticated statistical methods with molecular data, such as, for example, Bayesian and maximum likelihood, as opposed to maximum parsimony, which we typically use for morphological data, although that is starting to change now. So for these reasons, we typically consider molecular data to be probably giving us a more accurate estimate of topology than morphological data in most cases. When we build trees using these two different types of data, they quite often conflict with one another, which raises the question of how well morphology actually tracks evolutionary history if we use molecular data to be a kind of benchmark. There are several issues that affect morphology, probably more than they affect molecular data. And these are issues that are quite often associated with strong natural selection on morphological traits, often due to shared evolutionary pressures and occupying a similar niche. One of these issues is convergence, whereby species that aren't necessarily very closely related evolve independently to be morphologically very similar to one another, again, often due to shared pressures and sharing a shared niche. A classic example of convergence would be the anolis lizards of the Caribbean islands, of which there are several distinct, discrete ecomorphotypes on each island, each occupying a slightly different lifestyle. Molecular analysis has revealed that each of these ecomorphotypes, roughly, is more closely related to a different ecomorphotype on the same island than to the same or similar ecomorphotype on a different island, showing that these morphotypes have arisen during the course of evolution independently several times. However, cluster analysis on morphological traits on these lizards clusters these ecomorphotypes together. So this is an example of how convergence can mislead phylogenetic analysis. A related issue with morphological data is the non-independence of morphological characters. So sometimes morphological characters evolve together in semi-autonomous suites or modules, we might call them in a morphometric context. And again, this is quite often associated with finding particular adaptive peaks that are associated with a particular niche. So it's quite important to evaluate how widespread these issues are in morphological data, especially when considering the phylogenetic placement of fossil species for which we typically only have morphological data. So previously I've looked at homoplasy or convergence in morphological characters. So I systematically searched the literature for bird and squamate morphological character matrices from several sources. I then extracted these matrices and edited them where that was necessary. And I chose my final group of matrices on the basis of taxonomy, number of taxa, number of characters, etc. I wanted as wide a taxonomic spread as possible with as little taxonomic overlap as possible. And I ultimately ended up with 29 usable matrices for birds and squamates. And for each of these matrices, I optimized all morphological characters onto a molecular tree for squamates or a set of molecular trees for birds. So in particular, I calculated a support value known as the retention index, which is just a measure of how well each character fits onto a tree. And I averaged this across trees for birds. I then split my data into partitions, firstly osteology and non-osteology or soft tissue characters, and then I split them into finer sub-partitions of cranial, postcranial, integument, myology, and plumage. And I then calculated and compared the mean and ensemble retention indices between these morphological regions. So I found that osteological data fits the molecular trees better than the soft tissue characters or non-osteological data. So on this graph, each data set is represented by a point, with birds in red and squamate reptiles in blue. The y-axis is the average retention index of the non-osteological partition, and the x-axis is the average retention index of the osteological partition, and the line is just x equals y. So all of the data sets falling below that line are where osteology fits molecular trees better than the soft tissue characters. And this was highly significant both for birds alone and for birds and squamates together. Not for squamates alone, but I suspect that might just be because I didn't have quite enough data sets for squamates. I didn't find any significant difference between any of my sub-partitions of cranial, postcranial, plumage, integument, or myology. So this result may indicate that evolutionary pressures are acting differently on these different morphological regions. And also osteology appears to be tracking evolutionary history better than soft characters or non-osteological characters if we accept the molecular data to be a kind of benchmark. I've since moved on to looking at character correlations, so in particular whether the percentage of correlated morphological character pairs differs significantly between these same two partitions, osteology and non-osteology, and also whether the presence of correlated morphological characters affects phylogenetic reconstruction. Additionally, I've asked how sensitive my model-based methods are to the amount of data present in my data sets. So I've used a tree-based method for detecting pairwise correlations in all of my data sets, again using these same molecular trees as a benchmark. And I've applied 3 models of character evolution to all pairs of characters in all my data sets. So this model-based approach relies on the theory that if 2 characters are correlated, the rate of change of one character from, for example, state 0 to state 1 on a topology will depend on the state of the second character with which it's correlated. So of my 3 models, one of them is an uncorrelated model, which is an equal rates model, where all of the rates in this rate matrix are the same. And of my 2 correlated models, one of them is a symmetrical model, so the rates in the top corner will be different from the rates in the bottom corner. And my 3rd model is the all rates different model, where all rates in the rate matrix are different. And I compared these 3 models by using the AICC. So for each of my data sets, I ended up with 3 pairwise symmetrical matrices of AICC values, from which I was able to calculate the AICC weights. And then I just added the AICC weights for my 2 correlated models to get the cumulative AICC weights for my correlated models. And I used a 0.95 threshold to assess correlations. So I was then able to calculate the percentages of correlated character pairs both within and between my partitions. I then also compared the mean cumulative AICC weights within my data sets. And I then started to conduct a sensitivity analysis to see roughly how many taxa you might need to detect correlations that are there. So I found very few correlated character pairs in my meta-analysis in comparison with similar isolated studies that used very similar methods to mine. In some of my data sets, there were 0 correlated character pairs either in one or in both partitions. And I also found no significant difference between soft characters and osteological characters. There does appear to be slightly more for soft characters, but this wasn't significant. In terms of within my data sets, looking at the mean AICC value, there were some significant differences in some data sets between non-osteology and osteological data, but there was no overall consistent pattern of one partition being more correlated than the other. And in terms of my sensitivity analysis, I was able to detect strong correlations in highly asymmetrical trees at around 20 to 30 taxa. And I was able to detect fewer correlations in random, less symmetrical trees. Both tree shape and especially the number of taxa are probably likely to be important for detecting correlations. So I suspect that my methods are quite sensitive, in particular to the number of taxa in my data sets. And there does seem to be a slight trend of increasing number of, or percentage of correlated character pairs with increasing number of taxa within my data sets. So I'm going to continue with my sensitivity analysis and conduct them with different tree shapes. I'm also still continuing with analysis on some much larger data sets with much larger number of taxa. I found no overall difference in the number or percentage of correlated characters between partitions. And the presence of correlated characters raises questions about how this impacts phylogenetic analysis. And I plan to test this by reanalyzing morphological data sets, removing correlated characters. Thank you.